Hello and welcome to the Vector virtual session about software testing in accordance to DO-178. My name is Ingo Nickles. I am field application engineer working in that area and helping customers with technical issues since 2012, which is almost or even more than 8 years now. How time flies when you're having fun. I will say something about software testing and how to fulfill the requirements regarding software testing as they are described in the DO-178. I will also show some practical examples, and we will go even one step beyond and not only look at the pure requirements and how to fulfill them, but even look at how to optimize the test environment, how to integrate into a continuous testing process or environment, and how to integrate into DevOps. Well, some parts of the next minutes will be specific to the DO-178, specifically when we talk about the requirements and as they are described in the standard. But most of these things is focused on software quality and not necessarily just one standard. So even if you have no safety requirements or if you come from a different industry, I hope that there will be some elements of interest for you in the next minutes. So here we go. First, some words about DO-178. Now, the first version of DO-178B was published back in the 1990s, 1992, and during its lifetime, several other papers, clarification papers, were released, clarifying critical aspects of the document. And then 20 years later, 2012, DO-178C was published, and it integrates multiple improvements as described in these previous cast papers, for example. And also it came with multiple 4 supplements, for example, talking about tool qualification considerations, which is, of course, of high interest for us as a tool seller, as a tool vendor. We need to qualify our tool so that you can use it in your projects. There are some interesting sections in the DO-178, specifically for someone providing a software test tool. And these different aspects are listed here. I will not go into details of each of these sections, but one of the things that I will point out here is the requirements-based testing. So it is important in the DO-178 environments to have a requirements traceability and to do functional test cases, to not derive test cases from the coding, but derive test cases from your requirements, from your functional requirements. And also there's something important about coverage. We do have to have structural coverage or code coverage, and we do have to have requirements coverage. That means we should have test cases for all of our functional requirements. Then DO-178 spends some time on explaining the test process in different levels, in different flavors. You should have a low-level test where you test a single function or a single file isolated from the rest of the code. And then you can do a high-level test or software integration level test where you put multiple C files into one test environment and see that your subcomponent works as expected. And then in the end, we have the full system test with the whole software. Also, the DO-178 clarifies that you should measure code coverage and also which level of code coverage. And the level of code coverage is linked to the criticality of your product. The higher the criticality, the more code coverage you should measure. Now, what I find interesting is that this idea of criticality can be found in almost any standard that we looked at, and also common for all standards, not only avionic, is that the higher the criticality, the more code coverage you should measure. And the idea is that by measuring a higher level of code coverage, we will also expect to find more issues, to find more problems, to find more bugs in the software. So we believe that the coverage helps by finding test cases and by finding bugs with the execution of these test cases. And coverage is not just something that you need to do to fulfill to have a checkbox mark. It also helps in improving software quality. So even if you have no safety requirements in your product, you can still want to measure code coverage to increase the software quality. Now, how can we help with vector tools? We've focused in this session on the right side of the V model, on the testing part of the V model. And my personal focus is on the product Vectorcast, which can help in unit testing and in software integration level testing. And we can measure code coverage in all of these levels. We also help with test-driven development, if you were interested in something like that. And then we can run test cases on the host, on simulator, emulator, or on the real embedded target chip. And we can measure coverage in all levels of testing up to and including system level testing. There are some points as required by DO-178, which we can fulfill with Vectorcast. We can help with low-level and high-level test cases, as I said. We automatically can build unit test environments and software integration test environments. We can help with measuring coverage of in all types of testing, in unit integration and system level testing. We can measure statement coverage, decision coverage, MCDC and masking MCDC coverage. There are also ways of measuring function and function call coverage, but those are, as far as I know, not required by the DO-178. There is a help in providing requirements test case traceability. We can import requirements into the tool and then link them to test cases, and then we can export test cases and the linkage to the requirements back to your requirements management system. Also, we can help with data coupling, control coupling, not only by analyzing the code and creating reports about what couples do exist, what data couples and what control couples exist. We can also help with dynamically verifying whether when running test cases, the couples were executed in the expected ways. We can certainly help with tool qualification as far as Vectorcast is concerned. So if you want to use Vectorcast, then we have a qualification package, and it can be used to qualify the tool in your test environment. And we have done this hundreds of times in different projects since the 1990s. So these are things that are mandatory. Then we have multiple things that help to improve, and we continue to improve our product in terms of usability, in terms of additional automation. Whatever can be automated should be automated. And that's why we spend a lot of effort in automation aspects and also in optimization. What that means is, for example, we allow a parallel execution of your test cases. If you have multiple unit test environments, then they can very well be executed in parallel and on different kernels of your PC, for example, or on your continuous integration server, and then split to different machines and execute there, so that you reduce the time it takes to run all your test cases. Also, we can help with something that we call change-based testing. That means that when changing code, then we can identify the test cases that are affected by the code changes, and then we can incrementally only rerun those test cases affected by the code changes, which of course helps in saving time, and saving time is usually also saving money. And you get quicker feedback on potential bugs in your software. So how does this work in unit testing and software integration level testing? For example, we analyze your source code, then you can decide what is the file or what is the package or what are the files that you want to test isolated from the rest of the product. We then build a framework around the code under test, which is a test driver, which is stubs, and also you can add your some startup code or whatever you need to run something on an embedded chip. And Vectorcast builds source code to create this unit test executable. And then we use your compiler to build a binary of this unit test application, an ELF file or an hex file, or if you want to run under Windows or Linux, then a host executable like an .exe, for example. We then execute the test cases dynamically, get the coverage, get the results, and create reports in Vectorcast. The change-based testing idea is to say if I do a source code change, then it is usually not necessary to rerun all test cases, only those that are affected by the source code change. And by immediately executing all test cases by continuous testing, you get instant feedback because you run less test cases, you fail faster because you find the bugs quicker. And then we believe that the software developers will quicker get feedback on the problems that the new code brings. And this means we find the bugs in the software quicker. And by quickly finding the bugs in the software, we can reduce the cost of fixing the bug. So we spend more time on software quality early in the project because we are very close to introducing the source code. Testing activities is not something that is done at the end, which is a typical quality model. It is done very early. On the right, we see an example of an SCM source code management commit process. So if your developer wants to commit a software change to the base, then these are automatic steps that could be executed. And one of them is the executing all existing test cases, which is, of course, most likely taking too much time. But if you do this change-based, if you only rerun the affected test cases, then this is something that can perfectly well be done. So this is the theoretical part of my session. Now let me show you some things in action. Vectorcast, this is a test project. It's a small project. We only have 3 or 4 files in our project, but you get the idea, I hope. We can manage our testing activities in this one project. Also, we have multiple variants of different compilers where we can run the same test cases on the same source code, but being compiled with, for example, different compile defines or executed on the host or on the real chip. So the idea is to create test cases in one variant, and then the tool can automatically rerun them in different variants on different chips with different compilers. This is also helpful if you want to integrate into a DevOps process. If you want to continuously test, if you have a continuous integration server, then you can just provide this test project or you can put it to version control, and the continuous integration server can grab the code and the test project. And then we have a command line interface that can help you to incrementally build all test environments and to incrementally run all test cases. Now, this was very quick because we did not change anything. If I change a C file, for example, if I do a quick code change, which would usually come, of course, from version control, or you use your IDE to change your code. But then we see a tiny little yellow exclamation mark saying there is a change to some source code. So this affects a test environment. And now when we do the incremental rebuild, then we will have to recreate this one unit test environment. And we should also see that we need to rerun affected test cases. And we will only rerun those test cases that are really affected by the source code change. Now, when we look at some report functionality, we can, for example, look at the code coverage. And we show the code coverage per function, in this case, per subprogram. You can also sort and filter. For example, we can sort depending on the cyclomatic complexity and see what are the most complex functions in our code. And also we can look at the code coverage that we achieved on different files, on different functions. And then when you hover over the lines, then we show which test environment executed this line. Now, if we want to increase the code coverage on one of these files, or if we want to create a new test environment, then this is very simple because we already have the compiler configuration, we already have our testing project. We just need to create a new test environment. And then you see that step number 1 is already skipped because we know the compiler, because we take it from the test project. But just so that you see the list of embedded compilers that we support, it's more or less everything that that is out there on the market regarding embedded compilers. And of course, you can also run your test cases dynamically, building the test environment using a native compiler like Visual Studio, for example, or a GCC compiler. Now, we need to have a name for our test environment, and then we need to tell Vectorcast what is the file that we want to test. Also, we can handle stubbing. Should we stub everything that is implemented outside or nothing and use the real code, or do you want to customize the stubbing? We do not go into details of this, but there is a huge list of options how we can deal with stubbing and not stubbing. Now, when we say build, then this automatically builds our unit test environment so that we can create test cases and run them, execute them dynamically on the code under test. So this is our unit test environment. We see the name of the test environment. We see the name of the C file. Here we find the functions that are implemented in the C file, and this is created dynamically after analyzing the code. Now, one simple test case is a call to a function, and this is your way to create test cases by providing input values for the function parameters. Also, you can pre-initialize global variables and put specific data here. Now, let's, for example, call the function with table1 seed1. Then there is a parameter order with enumerations, and you can choose from a drop-down how do you want to call the function under test. We can check expected values, of course, for return values, but also for stubs that are called when executing a test case. And for example, I know the place order will call the function getTableRecord. GetTableRecord is not part of the code under test. That's why Vectorcast automatically created a stub, and we can ask the stub to verify the past parameter. And we can also tell the stub to return specific things that we want to have for our test. And this is how you can specify input and expected data. Now, by executing the test, we dynamically exercise the code under test, and we see that we get a passing result. The test case passed. We see that we called the function under test. We called a stub, and the stub verified parameter table, which is value 1, which is what we expected. And then it returns from the function under test, and we validated the return value. Now, the last thing that I want to show is code coverage. How do we display code coverage? And we show the structural coverage on the source code. we show green lines for lines that were executed, red lines for lines that were partly executed, and then yellow for lines that are partly executed. Yeah. This is how we display MCDC coverage. And for MCDC, we also analyze the truth table of every condition in the code, and we help in finding test cases for MCDC code coverage. And if you are in safety critical environments, then you have to have 100% code coverage, but it is sometimes very hard to get 100% code coverage. And that's why we integrated a coverage by analysis editor. So this coverage comes from executing the code. But if there is a piece of code that is hard to reach or impossible to reach, then you can use the coverage by analysis editor that allows you to manually check the checkboxes and say these lines were covered by analysis. We can write a justification and say this is the reason why we could not execute the code. This is the reason why it is still important, needs to be there. And we can save the coverage, and then the lines become green. They become covered with a different coverage indicator, which is the A here instead of a star for coverage indication. And when we look at a coverage report, then we see that we display the coverage in a different color. The coverage that came from analysis, and also in the metrics at the end, we show, or we distinguish, we make a difference between coverage that came from execution and coverage that came from analysis. And this is the end, my friend, of the Vector Virtual session about software testing according to DO-178. Thanks for joining.